Okay, let's start now. Uh, Recording has been turned on. Uh, it's 11 hours and 2 minutes a.m., 20th of June, and today is Saturday. Uh, पहले मुझे ये बताएं कि how many of you have received the official emails? UOP domain में किस किस को ईमेल मिला है? अपनी टेक्स्ट बॉक्स में yes और no लिखें। और किस किस ने चेक किया है कि ये ईमेल आपका काम कर रहा है, लॉग इन हुए हैं उसके ऊपर और कम्युनिकेशन उस पर पॉसिबल है। ओके, Abbas says no, you haven't received the email list. Razia said yes. Okay, so you better, those who haven't received, check out with the Dr. Uzair that or your CR rather, CR से आप कम्युनिकेट करें और उसको लिस्ट प्रोवाइड कर दी गई है। मेरे पास सिस्टम में एडेड है, सो इसलिए बट आई वंस sent the notifications, but I think it is not active at the other end. Have anybody logged into the email? यूओपी के ईमेल को लॉग इन हुआ है कोई? क्योंकि some students were complaining that they were able to log in, because एक्टिव नहीं था ईमेल पोर्टल पे, मे बी। Okay, boy is Islaudin again saying that he hasn't. So you contact your CR, contact CR से contact करें और वो आपको बता देंगे ईमेल एड्रेसेस आपके, क्योंकि फ्यूचर में अभी नेक्स्ट मंथ हो सकता है ये मैंडेटरी हो जाएगा। जो हमारी LMS पोर्टल है उससे आपको ईमेल से अलाउड होंगे। LMS portal is means LMS means Learning Management System. The same online teaching will be now migrated in a way पोर्टल। उसमें ये है कि आप ऑनलाइन एग्जामिनेशन सिस्टम सारा उसमें बिल्ट इन है। हम उसमें आपका असेसमेंट और क्विजेज एंड दी MCQs ये सारे ऑनलाइन सिस्टम उसमें फीड कर सकते हैं और आपको असेस कर सकते हैं, एग्जामिन कर सकते हैं। उसमें सारा टाइमिंग, सबमिशन टाइम, डेडलाइन, रिपोर्ट्स और सारा उसमें ऑटोमेटेड होता है। तो वो इसलिए LMS जो प्रेफर किया गया है और सिक्योर होता है। हर पर्टिकुलर लेट्स से 2 आवर, 3 आवर या 1 आवर जो भी टाइम दिया जाए उस टाइम के दौरान जो है पेपर सबमिशन होती है, उसके बाद एक्सेप्ट नहीं होती और ग्रेडिंग भी वो खुद करता है सिस्टम। मैनुअल भी है और ऑटो भी है। ओके, सो लेट्स स्टार्ट विद today's topics first, and we will come on with the discussion session later, the problems in the earlier topics. So this week, let me share first the screen. I have to join myself as well. Let me join so that I can see the sharing is enabled. Where is here the Google Meet? All right. So I think the screen is shared now. So let me take the first topic was, yes, this is the in order 3 topics were assigned, and I think in day before yesterday on Friday I changed one topic, which was the actually the order was the not proper, so I incidentally took the later topic at the earlier, but I just changed. Anyway, we can discuss the later as well, that you can, if you check those topics, the one topic which is a special devices, field effect transistor was changed. That is MOSFET was given, but the field effect transistor was supposed to be there. Okay, we are in the oscillator section. If, as you know, we previously discussed the oscillators. First we discussed the working principle, then the oscillator circuits, and then the two popular oscillators, Hartley oscillator and Colpett oscillators, we discussed in the previous sessions. Today we are going to discuss two oscillator circuits, which is popularly known as the RC phase shift oscillator or RC oscillator circuit. R and C, it is the major components which are playing a very important role. R and C, resistor and capacitor. RC phase shift oscillator. The other one is this one is the crystal oscillator. Crystal is used here. The crystal oscillator provide you a stable resonant frequency. These are two oscillators we are going to discuss. And the third one is the field effect transistor. We call it junction field effect transistor, JFET. Its construction and operation will be discussed over here. So let me take first the RC phase shift oscillator. Okay, we move it. Okay. All right. The oscillator, obviously, we have defined what it does. It converts DC electrical energy into AC electrical energy. So, in fact, the basic working principle we went through was that in the RC tank oscillator circuit, RC tuned oscillator circuits, energy was oscillating to and fro between the capacitor and inductor. But here you don't see any L inductor. You see C but no inductor. So that part you have to look into that. I will be discussing. I have discussed this in detail in my video lecture on the YouTube that I have discussed over there. Okay, so at anyway, here I am going to again explain. And just we are going through the review, quick review. I have provided you all the relevant material literature in the form of PDF. These files are available already, I told you, and in the form of video lectures. So basically, this is supposed to be a follow-up class, but since I have asked most of students, they say that they haven't studied those lectures. So that's why I give you the full 1 week in advance, the notification that go through those video lectures and the PDF files and study those lectures. You have got almost from Monday to Thursday, Friday rather. You have got the maximum time. Okay, so 5 days you study those lectures, watch those videos, and write down your questions, your queries with you, and come up in this follow-up class. This is a follow-up class. Okay, so we would discuss here the whatever the issues you have got. Okay, let me take the attendance. I have to take the attendance. If I don't take, then actually it is not saved over there, so I have to save it so that can have, although we have the automatic saving address, but there is a HTML saving which gives you the instantaneous connectivity time session every minute that which student has been stayed connected with the Google Class Meet, and how many hours or how many minutes that is being marked over there. Okay, so here we are, the RC phase oscillator. I will discuss that. This is the oscillator which is not a LC tank oscillator, right? It is a sinusoidal oscillator, one thing. So how we get this the oscillations which are the produced and the AC signal is converted from the DC. So what we have in this case, I would like, let me see if we have that graph I have discussed in the video lectures. This is let me go to the oscillator section. Third, I suppose it should be somewhere here in the files. Yeah, here it is. All right, here we are. Uh, so what we, if you remember when we were discussing this, what is this? This is the output characteristics curve of a typical transistor amplifier, and it is the obviously the common emitter, which is we can see VCE is here, IC is here, VCE and IC are the plotted here, and while keeping for one particular curve the base current constant IB is. So if you remember, uh, I discussed that while we were in the amplifier section, we were discussing the graphical treatment of the amplifier, how we uh, explain the amplification. Over there, what I emphasize that the job of the scientist or the manufacturer is to keep, this is the Q point, which is called quiescent point, and it is supposed to be quiet. Quiescent means quiet. It should not be oscillating or moving up and down. Uh, we can reduce this oscillation to a minimum level, but we cannot 100% bring this Q point to a halt or a zero level. That means it should be static over there. Why? The reason I told you already. This is the transistor is made of the semiconductor material, which is silicon or germanium. And intrinsic semiconductor material, silicon or germanium, they have this characteristics that at a room temperature, the electron hole pairs are generated continuously with the ambient environment or the surrounding environment, and their recombination is going on. Generation and recombination of the electron hole pair is going on regularly with the temperature. Higher the temperature, higher will be concentration of the electron hole pair. And I also told you, after doping and fabricating this semiconductor N type or P type, and then we join those two, still we follow actually basically we achieve the doping level with the narrow energy band gaps, but still there is this we call it minority charge carriers, which is intrinsic behavior where with the temperature electron hole pairs are being generated, they still remain there. So these minority charge carriers, I don't have here the IB is equal to 0. It should be there, which is close to the almost, they have shown it 0. IB is equal to 0 means IC is 0. We don't have any leakage current. So in the cutoff region are the region which is at the let me draw that. I'm feeling uncomfortable with that. I can draw it. Okay, I'll turn it off. The line I have to draw that. So suppose this is the, rather I take a line. That is the, now IB is equal to 0. Okay. This is IB. Let me make that. Let me make it capital. It is capital. So this is the point where base current is 0. Let me put that somewhere here. Okay. That. Suppose here. So with that. So that is equal to 0. Okay. So that is the cutoff region. Let me save it. and bring it on the maximum screen. All right. So this is the cutoff region. In normal circumstances, what we do, we keep this the cutoff region as low as possible. We don't want any agitation, any larger this cutoff region means the worst is the amplifier. Noise will be generated, and that is not good for the amplification. But what we have here, the in now RC phase shift oscillators, we are going to exploit this cutoff region factor contribution, that these tiny oscillations, the Q point is going up and down. We select such a transistor which has a large, pretty large cutoff region, and Q point is not stable, is going up and down, up and down. So oscillations, these oscillations are there. So in the RC phase shift oscillator, what we have, the those oscillations are fed back at the input, at the base of, this is the amplifier, typical amplifier, fed back, and they are amplified. Okay, let me see who is there. Okay, let me allow the students which are joining. So those oscillations, remember, now those noise are the noise could be due to some fluctuating voltage as well. You can, if you don't have a transistor, but you can provide a base biasing voltage which is oscillating, which is DC, is fluctuating DC, and that may cause the oscillation of the Q point up and down, and those oscillations are fed back and they are amplified, and we obtain a sinusoidal waveform at the output. So this is the basic, the main reason I have now explained to you, that we don't have L, then how we are going to get the oscillations. So RC role is different. RC job is, because when you have the, I have also discussed in the previous lectures in the class, when we are taking those classes before March, that an amplifier, when we have at the output, this output is out of phase by 180 degree. Okay, so in order to get now the regenerative feedback, if you remember, the scheme of the feedback scheme have two types: the positive feedback and negative feedback. Positive feedback means when the output signal is in phase with the input signal. So when you feed back the two signals, they are in phase, then we have the positive or regenerative feedback, which enhances the signal. So in this case, what we do, we get the we want to have a regenerative feedback. So RC phase shifts, three stage. So three-stage RC phase shift circuits are used. So I have also discussed this in the AC circuits, when we have the complex phasor diagram. When we have R and C, output is out of phase. We have rather done the number of experiments, rather one experiment of the phase. Luckily, the last experiment you have gone through, which was very important for the oscilloscope CRO, that find the phase or phase shifter we made from the RC circuit. So we have the technical hands-on. You have seen that technically in the laboratory as well, and theoretically you have also studied. We have discussed those topics. So you are lucky in that sense, that at least in the laboratory you have seen practically the phase generation, the change in the phase at the output across R. So what we do, we select a suitable R and C value so that it can, whatever the output signal we are getting at this particular across R is out of phase by 60 degree. So if one circuit RC is generating, again knocking at the door is there, but okay, it's dropped. Okay, so when we take the suitable RC circuit, so output, if you remember that what we have, it is the giving you the out of phase. So out of phase 60 degrees. So if we connect these three in series, they're one after the other, these three circuits, these capacitors, we have got one after the other. Then what happened that the last signal which we get is out of phase by 180 degree. So that's why it's called RC phase shift oscillator, which produces a phase shift of 180 degree here. So the RC phase shift oscillator uses, in this case, so that is the basic theme behind it. Okay, so oscillations are done through the noise produced inside the transistor, which is causing the Q point to oscillate up and down, and that is fed back, and that which is out of phase by 180 degree is brought back into the phase, so that that is amplified at the transistor, and output is taken across the collector. So the RC oscillator use a combination of an amplifier and RC feedback network to produce output oscillation due to a phase shift between the stages. So the phase shift is particular for the RC, but we have oscillations are because of the noise. Okay, now let me go to, you read, this is the feedback circuit. Okay, so phase shift is taking place from the output we are taking and giving it to back to the input, phase shift. So that is there. So read that circuit out. Here the again further detailed phase network which I have discussed. The first phase 60 degree, then 60 degree, then 180 degree. Total 180 degree phase shift is produced. Actually, I'm going to take the, okay, the now the frequency, the reactance is given xc over 1 over 2 pi r, the omega c, so which is equal to 2 pi fc. So if you take the phi phase is tangent inverse of xc over r. We have done this in the AC circuit analysis, the electronics, with a chapter, a second chapter after DC, rather second section of the syllabus. Okay, so that is the again the phasor diagram that is explained in the this document, and this is the same network which is given at the topic at the top. There's a slight correction I have made. Maybe there's in the editing of that document they have produced. Now here is the actual RC phase shift oscillator. I was actually coming to that. This is the typical how in the circuit we use this transistor has been used in the previous block diagram as an amplifier, but here now this is now typical. What is this? This is in common emitter NPN transistor amplifier with a self bias board configuration or self bias configuration. So what we have, this is called the RL or RC. Normally we call it RC, the collector resistance. This is the potential divider R1 and R, in this case R2. Instead of R2 we are using R, the one branch of the third stage RC circuit. And these two, job of these two resistors is to provide the base current, Q point value of the base current in the DC mode. Okay, so this is the emitter resistors. The job of the emitter resistance is to bring the stability in the Q point, although we have oscillations over there in the normal amplification, during amplification. And this is the collector resistance or the load resistance. It has been labeled as, this job is to provide the Q point of the current of the collector current. And this is the collector capacitor, which is used to block the DC going into the any other load or which you have connected the output source, and allow the AC comfortably at the output. Job of this capacitor is to ground any signal which is dropped across the emitter resistor, which may cause the reduction in the gain at the output. So that is the emitter capacitor CE. Now this is again, you can see it is the positive feedback right from the collector. The output is taken, and this RC phase shift oscillator circuit also work as a sampling network as well, which reduces the size of the from the output to the smaller size in case it is amplified and the large signal is obtained. Then small portion is only control portion, which is due to these all these three resistors connected. uh, the RC phase shift, these RC networks are in connected in a series, but the if you see R and C over there, the resistors are in parallel and the capacitors are in here in this case are in series. So that is the main theme that RC phase shift network works. So you have to explain in the exam if it is asked that elaborate or discuss the working mechanism of the RC phase shift oscillator. Then you have to discuss each and every component of it. Obviously, we have discussed this part at large in the introduction. Now, while these have been also discussed in the amplifier section, and I have also mentioned these now in this session as well. So that is all about the RC phase shift oscillator. Let's see now some. You can see here the relationship is given like that. If the three resistors are equal in value, if they are all of them are equal in value, that is R1 is equal to R2 is equal to R3. The capacitors C in the phase shift are also equal, C1, C2, C3. Then the frequency of oscillation produced by the RC oscillator is given by Fr is 1 over 2 pi R and square root of 2n. This is a relationship which is used to the n is the number of RC stages. Where so you see that where three stages are there, so 3 to the 6 square root will be used. So n is the number of RC. We use only here obviously three stages to have 180-degree, but if you want to achieve certain the wave shapes, then you can change these stages as well, 4, 5 or 6, whatever. So you can have that number as well. So that is given under root 6. And similarly, it is giving example, if there are 4, then it is 8, and so on and so forth. Okay, so let me take the attendance. Whenever the number is increased, I do take the attendance time to time. Okay, we have got at the moment 14 maximum, but still that number is very low as compared to the strength of the class. Strength of the class is 34, so we should have maximum number of students. Okay, so here we have the relationship is now defined, and that's it. This is the topic. This is op-amp operational amplifier. At the moment I have left because of the limited time, but I have given the documentation on the net. We will see if we have got time, then we will discuss that operation amplifier. Operation amplifier means which performs the sum and the subtraction operations, like summing of the signals, adding of the signals, and subtraction of the signals, two signal differentiation. So that is the operation amplifier symbol, and the rest is the same, RC phase shift oscillator, but we will discuss that later on. So that topic concludes here, okay, up till here. Here. So that is the RC phase shift oscillator. I will go through first these topics, and at the end I will ask you to, if you have any questions, we can discuss so that we can have, don't lose our time schedule. Okay, now this coming to the second is the crystal oscillator. Let me check if okay, crystal oscillator. One of the most important features of any oscillator is its frequency stability. So in this case, what we have, we can use any other type of means. In this case, we also take the oscillations, like we have the noise or the LC tank. These oscillations are fed back, and then those the oscillating signals which are being produced, they are not stable normally, whether it's LC tank circuit or it is whether in the RC phase shift oscillator. So the frequency of the oscillations may shift from a certain range, initial to final. So the one of the most important crucial feature of the important feature of any oscillator is its frequency stability. In other words, its ability to provide a constant frequency output under the varying load condition. Varying means variable load conditions. At the output, whatever you are feeding this, the oscillating signal, it might load, variable load condition means the resistance of that, the load, if it is varying, then the obviously the frequency may get destabilized. So oscillation stability in the oscillating frequency is the prime importance. This is the particular crystal, quartz crystal. This is in capsule or cased in the metallic. The two terminals are there. We are going to discuss uh, the right. You read out all this literature I have provided. I will discuss the main theme, that what is the basic working mechanism and the construction. All right. So here we have, this is the, I have drawn, I think somewhere. Let me check that. If I have the equivalent circuit. Okay, if I don't have it here. All right, let's see. All right, I have written over here. This is the typical crystal. Okay, let me draw if I have the tools. Okay, let's leave. Okay, let me turn on the tool draw a minute so that easily I can have the drawing procedure. All right, should be having drawing over here. All right, circle with the red. All right, so where is the crystal? So, oh, I don't think that is going to work anyway. So this is the typical crystal which I showed you here, and that at the top, that was the in the steel metallic uh, casing. That is, the case means the cover that is enclosed inside container, which is the made of the metallic steel. But inside, what we have two metallic plates. This is the metallic plate, like a capacitor. This is also a metal plate. And we place a quartz crystal over here, crystalline, obviously. Quartz crystal, very well-known crystal, placed over here. So this is now the actual crystal structure. But what happens, the internal parameters, if we look into it, what we have, they form an LC tank circuit. Okay, so here we see that the equivalent electrical circuit, this is now called equivalent LC tank circuit, which is comprising of this is the capacitor. The internal crystal act like a capacitor as well. There are two capacitors actually, which is the CS, we call it series. The internal crystal has the two planes of a crystal, opposite planes. They act like the capacitor, which called CS, and we call it the series capacitor in the branch. And this is now called the mass of the crystal act as the LS, or the inductive behavior is shown by the mass of the crystal. C as the elasticity, obviously, to opposite the planes of the crystal, like we have the crystal in the cubical form, so we are opposite plane of the cube. They have the elasticity between these two planes. They act like the capacitive nature, and the friction in between the planes or the of the crystal is called the resistance. That is the resistance. So all these three are considered to be connected in series, making RLC series circuit. At the same time, there is a main capacitor which called the plate capacitor, P for the plate. This is the main capacitor. This is the main, which is the metallic actual capacitor. This is a physical capacitor. These are the virtual equivalent circuit. So the parallel capacitor is in the, sorry, the plate capacitor, which is the metallic plate capacitor. You can call it as a parallel capacitor as well, because it is connected in parallel. That is connected in parallel with this RLC series whole crystal circuit. So that is the main equivalent circuit, which will produce obviously the oscillations as well, and those oscillations will be stable oscillations. So the whenever we release the DC energy to this crystal, that DC energy sets the crystal into oscillations because of charging and discharging, charging and discharging. And RLC series circuit job is to maintain, if you remember, we have also done the RLC series circuit in the previous class, in the rather in the final class, in the second AC circuit analysis. That RLC series circuit, they uh, act as an acceptor circuit, a particular bandwidth of the frequencies. So they can restrict only a certain band of frequencies or reject other band of frequencies, certain bandwidth of the frequencies. So that's why it is used as a stabilized or stable frequency oscillator. This is the Z, means the total impedance will be the parallel combination of these two. Series combination of this Z equivalent, ZE, which is equivalent, which will be sum of all these three, but you should remember they will be added in the Z or the complex form, because they are the now the real and imaginary parts. We have L and C has a phase difference in the signal. So R plus J omega L minus J XL minus J XC. Okay, XC, that is the main equation for that. So, and this ZE will be then in parallel with the ZE of this, which is X1 over XE. This is XE, okay. So 1 over XE plus 1 over ZE is equal to 1 over Z. So Z will be calculated from this. So that is the main role, okay, of the, I'm just discussing the main theme, okay. The rest detail is discussed in the, you just in the this topic in the theory. Everything is defined over there. Similarly, you can see the relationship. I explained that the Z series resistance or Z equivalent is the sum of these R S square plus, this is the magnitude part, should have been in the bars, and the equivalent is now ZP, which is now the parallel combinations given by the ZS plus XCP ZS into XCP. So that is the equivalent capacitance. XCP means the P, which is the parallel plate capacitor. That is the main, the parallel capacitor which is connected along the parallel branch. So here is the graph, is very self-explanatory graph is given between frequency and the impedance. That one can see that in one case it is acting like the rejector circuit for the here, and in the other case it is like a acceptor circuit. But remember, this is a parallel resonance, this is a series resonance for Z, okay. But for the gain it will be inverse, it will be other way around. But for Z, obviously this is blocking these frequencies, and for the parallel it is allowing these frequencies. So for the Z, okay, so that is the, but here what we see that the frequency, rather it is not allowing, we can say that at parallel resonance the ZP is maximum, okay. So what does it mean? That at maximum impedance means the signal will be minimum, okay. So it will be blocked, it will be blocking this frequency over here, the at the when you take the frequency versus voltage or the gain. So higher the impedance means smaller that the current, smaller the current means smaller the voltage. And similarly here the lower the impedance means, which is only series RS left, means the higher the current, higher current means the higher the voltage. So for across RS, so that will be the main circuitry. Okay, so similarly the other graphs you can see again for the XCP, XS and XP, they are explained over here, which are again the self-explanatory. The inductor is the positive phase we have along this side, capacitor is the negative phase along the negative axis, that is there you can see, and the frequency along the x-axis it has been plotted. So now the resonant frequency is given by now f of, for the branch, series branch, is given 1 over 2 pi ls cs square root. So for the branch frequency that is over there, that will be given by ls cs square root into 2 pi, while the parallel resonant frequency fp is given by 1 over 2 pi ls. C is now taken with the parallel to the cs, cp and cs. So over there for parallel circuit, that is given by ls into cp, cs over cp plus cs. So actually for parallel what we have, the circuit's frequency is given by this relation. So finally we have, if this is some problem is given, that a quartz crystal has the following values: rs is equal to 6.4 ohm, c as series capacitor is 0.09 picofarad, ls is 2.5 millihenry. Then the across the terminal cp is measured as the 28.68 picofarad. Calculate the fundamental oscillating frequency of the crystal and its secondary resonance frequency. So first we calculate the series frequency fs, which is given by by putting the relevant values, 9.98 megahertz. Then take the parallel frequency, parallel plate, which is putting the values, which is the 10.05 megahertz. Then one can see that we can see the difference between the fs, the crystal fundamental frequency, and fp is small, about 18 kilohertz. That is the difference. If you take 10.005 megahertz minus 9 point, that is the upper and the lower frequency difference, which is 9.87 megahertz, which is equal to 18 kilohertz. However, during the frequency range, the Q factor of the crystal is extremely high because the inductance of the crystal is much higher than its capacitive resistance. From the values we can imagine that are the resistive values. So the Q factor of the crystal at the series resonance frequency is given by Q factor. We have also discussed that in the IC circuits. So that is given by XL over R, Q 2 pi F L over R. If you put the relevant values, you get the Q factor is 25,000 equivalent approximately. So that is I think concludes this topic. With this, we reach to the end of this topic of the crystal oscillator. Now we come to the last topic, which is the junction field effect transistor. Now these are special devices we are moving in. Okay, so we have so far you have studied the oscillator section is over. That is the 4 oscillators we have discussed. So that is complete. We are now in the next section of the syllabus, which is called the special devices, or we can call the field effect transistors. All the transistors, they work on the basic principle of the electric field effect. Okay, so the this is the typical field effect transistor, junction field effect transistor. First, we will discuss the construction and working mechanism, and then we will discuss its various types of the this transistor. Okay, let me check that if I have rather that figure, proper figure for you. Field effect transistor should be in special devices. This is first. Rather, I have placed that somewhere on the. These two figures will be, yeah, here it is. All right. Let's now discuss first the field effect transistor. We will go back to that the lecture note as well. What we have, if you remember, the the previous transistor, which is popularly known as BJT or bipolar junction transistor, BJT bipolar junction BJT bipolar junction transistor. So B is for the bipolar and the junction transistor. Where two poles are there in the polarities, the N type, the transportation of the charge or the energy take place due to the transportation of the two pole polarities of the charges, N type and the P type. Okay, either P transistor or NPN. In both, we have two different polarity charges. So transportation takes place. But in junction field effect transistor, we have one type of the charge carriers which takes the energy from one point to another. And here is the typical example. The construction, what we have a one N type material, big bar, we call it channel. Okay, we'll name it as a channel. So field effect transistor means junction field effect. FET means F for field, E for effect, T for transistor. So the control of the current is made by the field effect. This is the main theme behind it. Okay. So in this case, the N channel bar we have got the N charge carriers are there. So what we have then what we do, we dope p-type material on this is the rectangular bar, length is greater than its width. Then on the two sides of the lengthwise, the opposite sides, we put, or rather we fabricate, we dope p-type materials, which are pretty highly concentrated over there. Normally it is at the middle of the bar. So what we see, we will see the three-dimensional picture as well. That this is a big bulk, rather the bulk material, which is N-type material, which is responsible for the transportation of the charges. So what happened that now we name these terminals. The terminal which is here is called drain. Here the other side is called source. Another terminal, these are the two p-type are connected with a single common terminal which is called gate. So it is similar to the emitter. Source is like emitter, and drain is like a collector, and gate is like a base. That's the same type, almost similar type. The three-terminal device. It is a three-terminal device, FET especially. So what happened that when we put the gate into the reverse bias mode, what will happen? If there is no voltage applied, if the voltage is zero, so what will happen? They will have the very slight, small, the depletion regions on the both side. And if we apply a VDD voltage between the drain to source, apply the voltage, what will happen? The current will flow from drain to source very easily, because now all the paths between these two P type is available. Path is not being blocked. But when the gate voltage is applied, what happens? This is a negative, this is positive with respect to this one. So this is positive with respect the on this side. This is negative and this is a positive from this side. So reverse biasing of these two junctions will take place, because the negative voltage will apply on the both side, both P type. So what will happen? These depletion region will stretch, expand. Okay. So expanding this depletion region will reduce the size of this channel, this region, and the less amount of the charges will be N type will be now moving. The drain current is controlled or reduced. So more and more you apply negative voltage, more and more the region will expand. A point will reach that these two the stretched depletion regions will touch each other. That particular stage is called the pinched off. The transistor is pinched off. Field effect transistor is pinched off. So you see that uh, the here the current is the drain current, which is the collector current in the previous case, but in this case, the drain current is controlled through a field effect. By applying the field across the PN junction, the depletion region expands and it reduces the current. Similarly, if you reduce the field between the PN junction, the region is now contracted or shrinked, goes back to its initial position, and the drain current is increased. So we control the current flow inside the material. So if you remember, whatever the device you take, semiconductor device, we are manipulating, we are controlling the internal currents, internal resistance. Here in this case, we are providing the resistance through the field effect. In other cases also, over there we had one junction was also being biased, positively shrunk, that was allowing, by shrinking that was allowing in the case of the base biasing of the bipolar junction transistor, so allowing the base current into from the emitter to base, and then from base to collector. So whatever mechanism you use, you like to, these are actually used for the high speed switching, control the AC devices, or the high load of the AC, the devices heavy load. The fast switching is needed in this case in certain operations, so the field effects transistors are used. Okay, so this is the basic working mechanism. This is the biasing, the diagram as well, so you can see the polarities are there. Okay, so let me come back to the topic. Now, this is the another, I will let you say the basic construction. Okay, that was the field effect transistor. Now what we have, this is again the similar another way of the construction of the field effect transistor. We have this a P type material. We have now make that the material is there, and the terminals are taken as a drain and a source, and there is a P type gate. These are two gates are connected with the negative voltage. Here negative is there, so that is also connected with this one. Okay, these both are the same, and they are the two drains, and the VDS is applied between the drain and the source. So actually this is the connectivity between this N-type channel. So whatever the main big bar is made of, or the bulk is made of, that will be called the N-type channel. Channel which is the path or the flow of the charges. So the you can see here by applying the negative voltage, the reverse biasing causes the region to expand, and these depletion regions will touch each other, and the transistor will be in the pinch off state. Okay, so why it is not going away? All right, let me take down. So that is being mentioned in this case. That will be there. You read out that. Let me show the. This is the pinched off. G50 is the pinched off stage. This is the pinched off. You can see both regions are now in the reverse bias. The touching now, the no current is possible from drain to source. So this is another way. This is the, you can draw it many ways. But I have just elaborated the cross-sectional view over there. That was a simple one. So these two gates, p-type materials, are interconnected together. So this is another example that we have the junction field effect. This is the N channel, which is being shown as a resistance, is being controlled by the gate uh, diode, which is making between the p-type and the n-type to p-n junction diode, and controlling the resistance of the n channel, the main bulk. So this is the volt ampere characteristics curve, VDS, the same characteristics curve which we have bipolar junction transistor. When we plot the family of curves at the output, we have output is the IDS, which is the drain current, and the drain voltage is applied, while we have the VGS voltage is in zero. You can see the maximum current because the less gate voltage is applied, so drain current is maximum. And the highest negative voltage -4 volts, suppose between the gate and the source is applied, the minimum current we have, the pinched region pinched off, we get in this case. This is called the knee voltage, where it from maximum value it goes to the stable value, constant value. So this is due to the internal charge carriers of the channel. Okay, the symbol now, this is the symbolic representation for the field effect transistor. This is JFET, junction field effect transistor. So this is you can see the particular type of the N channel, the inward arrow, this is a plate, and the right angle, these two terminals are now the typical symbolic notations of the junction field effect transistor. There is a combined, I think, a picture as well. Rest is, you can see the drain current in the active region is given by this relation. Okay, let me see the typical that was there. Okay, so that is the basic working mechanism of the junction field effect transistor. Okay, here we are. These are the two figures. This is the N channel, this is the P channel, junction field effect transistor construction. This is the N channel, the arrowhead is pointing inward, the P channel arrow is heading or pointed outward, as is the P channel. So these are the symbolic notations for the field effect transistor. There are two types we will discuss in the next class, because this class is getting pretty lengthy, so that I can take your question answers in these topics or in the previous topics. I will stop over here. So now come back to the main. All right, here we have, let me take the attendance again. attendance has been checked. All right. All right. So anybody have any question? Now I make this session open to all of you. You can write in the chat box if you have a question. I will then allow you to talk if you want to talk, or you can put your question. Any question? I was checking my mic. I hope you can, all of you can hear me. Anybody wants to ask any question, please turn on your mic. Okay. Saladin said, explain the drain. These are actually different symbols used, like in we have emitter and collector. Okay, so emitter is here is replaced as a name with the source, and the collector as a drain. Okay, drain where the source is supplying the charge carriers, and it is draining out, coming out. Okay, so it is just like that. Collector is collecting, and the drain is just draining these the output flow of the charges. That's what it seems that meaning drain have. But just to scientists have kept the two different terminals so we don't confuse it with that. Yes, it is output. This is just a collector. So then yes, it is. You are right. You can talk. You can turn on your mic on, and we can discuss. Now you are allowed to talk. Okay? Anybody wants to talk, turn their mic on, and they can talk. Okay. Any other question? Let me stop those other unnecessary things which are there. And should I think stop presentation as well? Okay, thank you. Okay, anybody else has any question? भाई किसी का कोई क्वेश्चन हो इस टॉपिक में या पिछले टॉपिक्स में, I told you that we can have it's not there's any restriction. Okay, previous topic जो किए हमने oscillators की किए हैं. I know you are gradually picking up, meeting the this is unforeseen, यानी हमारे पास अचानक ये situation आ गई. So we have to meet now, very tight schedule है, हमने इसमें करना है. So हम restrict नहीं कर रहे. It is open for all the topics you can discuss. So it is better to you go through those topics. ये ज़्यादा अपना पूरा ज़रा streamline करें, टॉपिक अपने रेगुलरली अटेंड करें, और उसमें जो है फिर इधर प्रिपेयर होके आएंगे तो आपको जो क्वेश्चंस होंगे जहन में वो हम डिस्कस कर सकते हैं. सो मुझे चैट में बताएं कि ऑल ऑफ यू हैव एनी क्वेश्चन और नॉट, यस और नो करें, ठीक है, ताकि सो कैन वी कैन कंक्लूड. Okay, good. Kiran says, is it clear enough? You can, it's not the end of it, okay? You can ask the question anytime, no problem. Now we are on the this internet connectivity. We have got the email, we have got the WhatsApp. On the WhatsApp, we have too many groups to handle. So very specific, very pertaining question you should ask. We may respond late, but through the email, but we have to handle a lot of groups and the classes and doing the homework for you people to prepare these things as well. So that may takes time, but we will respond. Obviously, email is the best way. Okay, and the new LMS system is coming up. That is the obviously very best way where everything is logged in, all the record is there, and that will quite help you a lot once you are on the LMS system. LMS means Learning Management System, University of Peshawar, where we will be shifting our portal. So I hope that no further questions. So we conclude here and close this session. Thank you, all of you, for joining. See you next time. So far, the same schedule on the Monday, the Saturday, sorry, on the Saturday of each week, from 11 a.m. to 12 p.m. Till then, goodbye and Allah Hafiz.